another example of work done by a non-conservative force. Now this up here, let me actually put this in another little bubble. This is kind of a big deal, this thing here. Okay, because this is always true, even when there is no non-conservative work done. This takes into account not only situations like this that have friction, but also situations that don't have friction. Okay, this is really, really a big deal. Okay, this statement right here. So we're going to go with this. When in doubt, if you're working a Chapter 8 problem, start with that, and you'll be good. Or you'll probably be good. 99 times out of 100, you'll be good if you start with that, with a Chapter 8 problem. So, here we go. We have a block moving to the right, speed 4.6 meters per second, mass of 1.5 kilograms, frictionless. Mu sub k is 0, so it's moving at a constant velocity until it hits a rough patch where there's a coefficient of friction of 0.42, coefficient of kinetic friction. Question is, how far does it go before it stops? So the initial point is it's moving to the right with speed 4.6 meters per second. Its final point here, F, is when it comes to rest. We want to know how far it goes, and we're going to use this to do it. Okay. Now remember that this is just another way of writing this is EF minus EI equals work non-conservative, because that's what delta E means, right? You know that. So let's figure out what these three are. Now look, it's not obvious where D is going to come from, right? We know we're looking for D. Where do you start? I don't see any formulas with D in it. Fear not. Go with this principle. Journey forth. You can't always know the path you're going to take. You sort of got to take a principle, trust it, and go forward. So let's do that. Let's solve for each one of these three things. See what we get. What's the final energy? Well, there's three different kinds of energy that we could deal with here. We could deal with kinetic energy. We could deal with gravitational potential energy. We can deal with spring potential energy. No springs here, so we can toss that one out. Two kinds of energy, kinetic energy and gravitational potential energy, remain. Now, the wise student, and that's all of you, the alert student, we'll call this height, y equals 0. So that the block is just moving in the x direction. It's not moving vertically. So for the entire time, it has no gravitational potential energy. None. Why? Because we called this 0. If we had called this y equals 13 meters or y equals negative 73 meters, we'd have to put a potential energy term in, because some of the energy would be gravitational potential energy. But if we call it 0, then all the gravitational potential energy terms go away, and we don't have to worry about it, because there's no vertical motion between I and F. It's all horizontal. So we can choose freely to call the height where the block is 0, so that the gravitational potential energy is always 0, and we're done with it. So the only kind of energy we're left with is kinetic. Is there any kinetic energy at the end? No, right? Then let me just be explicit about this. Maybe with a different pen. EF is, I'll get it right one day. EF is 1/2 mvf squared plus mgyf. All right, we're looking at this term here to remind you what we're doing. Starting with this principle here. So that's our final energy. But look, we've already defined the height of the block to be 0, so this is 0. Also, at the end, the velocity is 0. Okay? So there's no kinetic energy either. So look at that. We have 0 final energy. That's a perfectly reasonable, cool number to have. So don't be worried if you're working a problem and you get 0 for an energy. That's legit. So EF is 0. How about for EI? What kind of energy did we have before? Well, I'll go ahead and finish out what I've started here. My pen is dying. That is the sound of a pen dying, in case you're curious. Can you even read that? I guess so. If you sort of get close to your monitor and squint your eyes a little bit, maybe you can read this. So our initial energy, this term now, initially here, we have no potential energy because, as I've said now several times, we defined the height of the block to be 0, so no potential energy. So it's all kinetic. Okay, it's all kinetic. So the initial energy is just 1/2 mVI squared. We can find that number. I don't think I've actually found it, but we could find it. If you want to know the energy, we could find it. So what happens is we go from this much kinetic, this much total energy to no total energy. So what is EF minus EI, which is the left-hand side here? Well, EF is 0, EI is 1/2 mv squared, so that equals minus 1/2 mvi squared. And again, we know those numbers. We're given the initial velocity, 4.6. We're given the mass, 1.5. So that number is left-hand side, we know completely. It's very simple. Negative 1/2 mvi squared. Okay. So this is negative 1/2 mvi squared. Done. Except for plugging in the numbers and stuff. Now we have to think about this term. What is the non-conservative work done? Oh, Lord. I think I'm going to go over this afternoon to my backyard and have a funeral for my orange marker. A little bit of music, prayer, maybe. Somebody say a little few words for it. Let's see. Non-conservative work done. Well, that's going to be the non-conservative force acting times d times cosine of theta. I told you, and you have all done it. I know that you have. You've memorized that. Whenever you have a work, you can always write it as the force doing the work times d times cosine theta. What is the force doing the work here? What force is doing the work to slow this thing down? Well, let's imagine a free body diagram here. Yeah, we got time. Oops. When it's moving here, okay, what are the forces acting on it? Well, normal force up, mg down, and the kinetic frictional force to the left. It's moving to the right. Displacement is to the right. But F sub k is pushing to the left. Remember, the force of kinetic friction always opposes the motion. So if it's moving to the right, F sub k is to the left. Okay? And notice that N and mg are equal and opposite. Okay, they cancel out. So we can write this. Non-conservative force here is the force of kinetic friction. So force of kinetic friction, d cosine theta. But the force of kinetic friction is mu sub k times n, now d cosine theta. Okay. So all I've done is say that the non-conservative force acting here is the force of kinetic friction, F sub k. But F sub k can always be written mu sub k n. And in this case, The normal force has the same magnitude as mg. Those forces are equal and opposite. They cancel out. Okay? So we can write that the work done by the non-conservative force of friction is mu sub k times n. Watch closely. Don't get sleepy on me now. Stay frosty. N is mg. Times d times cosine of what angle? With this expression for the work, that angle theta is what? It's the angle between the force that's non-conservative and the displacement. Non-conservative force is F sub k that way. Displacement is to the right that way. The angle between them is 180. So cosine term becomes -1. So the non-conservative work done after all this work is minus mu sub k mg d. Okay, I want you to step through this, and remember, it's the frictional force doing the work, doing the non-conservative work. So I plugged it in there, and then I plugged it in and made another substitution, and yet another one. I want you to follow all those substitutions. So 1/2, and then we now have the right-hand side. That is minus mu sub k mg d. And what are we looking for, friends? We're looking for the displacement. It's right there. Like I said, follow the principle into the thicket. It will guide you, and you will find what you need if you stick with this. Find E sub F, find E sub I, find the work done by the non-conservative forces. Put them in, and now we can solve for everything. In fact, we don't even need to know the mass of the block. We can divide that out. It's common to both sides, both terms. We can also divide by -1 to get rid of our negative signs. And solve this now for D. D will be equal to VI squared over 2 mu sub k. Oop, not D. That's silly. That's so silly. Mu sub k G. We know everything. V sub I is 4.6 squared. Oops. My pen, my poor pen, times 2 times 0.42, I believe, times 9.81, and the answer will come out in meters. You do that, you get 2.6 meters. So that is our answer right here. D equals 2.6 meters. Okay, all we did, we found E sub F. We found E sub I. We found work done by a non-conservative force. Put them all in. Solve for the thing we're looking for. And there you have it. This you can bank on, friends. It's golden, solid gold. Not many of those things left in this world, but that's one of them right there. Take it home. Become friends with it. See y'all next video.